Hi, everyone. My name is Wilson Kong, and I'm a material science PhD student from Arizona State University. So today I'll be talking about some of our liquid metal-based soft composites that are used for thermal management applications. Now, thermal interface materials, or TIMs for short, are necessary components in order to eliminate the air gaps in between heat-generating components and improve thermal transport across different interfaces. And these TIMs are composites consisting of a soft matrix material with high thermal conductivity solid fillers. And the reason that these TIMs generally have conductivities of 1 to 5 watts per meter Kelvin is largely due to these point-like contacts between solid fillers, and these serve as scattering centers that impede thermal transport. And improving these contacts can be a way to address these low thermal conductivity values for TIMs. Now, TIMs are generally characterized using a thermal reference bar method, which essentially measures the thermal resistance across a sample material. And by knowing the thermal resistance of the material and the thickness, we can effectively calculate the effective thermal conductivity of the material. So for recent years, liquid metals have been an attractive interest as opposed to solid filler materials due to their liquid-like and deformable nature while also maintaining a high thermal conductivity. And a few disadvantages that liquid metals currently face is that they have relatively low thermal conductivity compared to other metals, but they also react with different metals and thus producing materials that may not necessarily be useful for TIMs. So in our work, we look at liquid metal and silicon carbide co-fillers for thermal composite and disperse these materials within a silicone oil through shear mixing. Now, silicon carbide we chose because of its high thermal conductivity and its non-reactivity with the liquid metal itself, as characterized through XRD. Now, we use silver-coated silicon carbide because they improve the wettability of the liquid metal on the non-wetting silicon carbide surface. So in this case, when we look at a comparison between the silver-coated and the non-coated particles, we see that the liquid metals adhere more strongly towards the silver-coated particles, and thus bridging multiple particles together through this wetting process, and not necessarily wetting as strongly with the uncoated silicon carbide particles. And this is important because by controlling the amount of liquid metal we add into the composite material, we show that increasing amounts of liquid metal can thus reduce the amount of thermal resistance that the composite experiences under a variety of loadings, and also increasing the effective thermal conductivity of these particles, composites, at increasing pressures. So the schematic shows that under an applied pressure that we can start bridging these particles together and forming improved thermal connections. So looking at across different spectrum of liquid metal compositions, we see that at 20 volume percent of liquid metal that we can achieve thermal conductivity of up to 10 watts per meter Kelvin, which is substantially higher than the base polymer conductivity of about zero point 0.2 watts per meter Kelvin. So in the future, we'd like to explore additional processing modes for these types of composites and to study cured elastomeric composites containing these co-fillers and studying the thermal, dielectric, and mechanical properties of these different types of materials. So I'd like to acknowledge the Semiconductor Research Corporation for their funding and also the Earring Center for Materials Characterization at ASU. Thanks for watching, and I hope you have a wonderful rest of the conference.